This is a sphere inscribed in a cylinder. It's a famous problem put forth by Archimedes in his book on the sphere and cylinder, written about 225 BC. In it he showed, with a lot of very difficult mathematics, that the sphere occupies exactly 2/3 of the volume of the cylinder which it is inscribed in, and has exactly 2/3 of the surface area too. What an interesting result. Archimedes was so excited about it that he had it inscribed on his tombstone. Well, today we're going to learn how to do some mathematics that can solve this problem too. Archimedes was considered one of the 3 greatest mathematicians of all time. So that's a pretty good feat, isn't it? To do this, we're going to draw on the work of one of the other 3 greatest mathematicians of all time, Isaac Newton, who invented the calculus, which allows us to do this much simpler than Archimedes did. Well, we won't quite get to this problem today, but you'll see similar problems, and I think next time we'll finish this up. But I wanted to at least whet your appetite to show the neat things you can do with multivariate calculus. So here's what we're going to talk about: triple integrals. So we can do integrals over volumes like that. The triple integral, you recall from last time, over a box B, which is the Cartesian product of the interval AB on the x-axis, CD on the y-axis, and PQ on the z-axis. So you get this box in 3 dimensions. Is defined like this. It's the sum over ij and k, delta xi, delta yj, delta zk, the dimensions of the box. We've broken it up into m intervals, n intervals, and p intervals, let's say. We can sum over those little volumes each of these times a weighting function f, which might be thought of as a density. Maybe this is the density times the volume of each little box. Estimates the mass of this little box, and then if you add up all little boxes with these sums, you get the mass of the big box that has a varying density over it. That's the concept, or you could actually think of this as a 4-dimensional volume. If f is the dimension in 4 space over x, y, z space, then you can think of this as the little subvolume times the distance in the 4th dimension, and you can get 4-dimensional volumes this way. So there's other applications too if you want to be abstract. We remember from last time Fubini's theorem, we can evaluate this integral, right? This is the definition of the definite integral in the, we said we could evaluate it. Fubini said for a continuous function f over a box, right? This is over a box, by taking an iterated integral. So this is different than this. This notation means this limit of the sum. This notation means an integral of an integral of an integral, with the inside integral treating the outside 2 variables y and z as constants, the middle integral treating the outside variable as a constant, and finally the outside integral just an ordinary integral of calculus 1. You can put these in any order also. We said there's 6 different orders you can do the integration, and it doesn't matter which one you do. So here's one more example. I did one last time. The mass of the box, let's say on 0 to 1 on the x-axis, minus 1 to 1 on the y-axis, and this should say 0 to 2, it went off the page here, on the z-axis. For a density function e to the 2x plus y plus z, what is the mass of that rectangular box? Well, we just have to integrate the density function of the box. We're adding up all these, but how do we evaluate it? We go to Fubini's theorem and rewrite it as an iterated integral. 0 to 1 in x, minus 1 to 1 in y, 0 to 2 in z, which is off the page again. So now, how do we evaluate the iterated integral? We first do the integral on the inside with respect to x. The integral of e to the 2x plus y plus z is 1/2 e to the 2x plus y plus z, right? This is e to the y plus z times the e to the 2x function, whose integral is 1/2 e to the 2x. So there's the antiderivative. Plug in 0 and 1 and take the difference. We get 1/2 e squared minus 1, all times e to the y plus z. Now we've got a double integral to do, e to the y plus z with respect to y and respect to z. So we integrate with respect to y, e to the y plus z. Oh, and it's just e to the y times the constant e to the z. Integral e to the y is e to the y times the constant e to the z. Gives us this for the integral e to the y plus z is e to the y plus z. Now we got to plug in minus 1 and 1 for y and take the difference. That gives us e minus e to the minus 1, right? E to the 1 minus e to the minus 1. And that leaves us just with the integral of e to the z dz, which is e squared minus 1 if you work it out. And so this is the value of the iterated integral, integrating the inside integral with respect to x, treating y and z as constants, then integrating the next integral with respect to y, treating z as a constant, and finally integrating with respect to z by calculus 1 techniques. Here's the next page. More generally is what we want to do. Who wants to just do rectangular boxes, rectangular parallel pipe as they're called in mathematics? In 3 space, suppose we let W be a more general solid. It's bounded by a surface on the bottom, z equals z1 of xy, on the top by a surface z equals, I should say z2 of xy. These are both continuous functions over a nice plane region, such as a horizontally simple or vertically simple region. Those will be the only ones we're interested in. You can do much more complicated ones, but these are the ones you'll be tested on that are in all the calculus books. So suppose the projection of this solid here, R, what calls it D, actually, is a vertically simple or horizontally simple region over which we can integrate doing a double integral. And here's our solid. If we enclose it within some big rectangular box, we can define the triple integral to be the limit of the triple sum of f hat, delta x I star, y, delta y, j star, delta z, k star, where f hat is equal to 0 if you're at a point that's in the box that's not inside the solid, and it's equal to the value of f if you are within the solid. So this adds up f times the volume of each sub-solid over this box. The details of this are not important, only the concept is. If you've got the concept, we're adding up f times the little sub-volume over all the little sub-volumes that are inside W and leaving out the outside ones. That's the idea. That's the definition of the triple integral, but how shall we do it? Here's the big theorem for triple integrals that are not over rectangular boxes, but over this kind of solid. It can be evaluated by doing a double integral, something we've already done, of the integral from z1 of xy, the bottom surface, to z2 of xy, the top surface. So you integrate from bottom surface to top surface, the double integral over the region of projection. That's how we evaluate triple integrals in practice. We'll call that equation 1 there if you look. Suppose we want to evaluate the triple integral of x dv, like maybe x is a density function, or the extension into 4 dimensions. If W is the tetrahedron, a figure with 4 triangular sides, and suppose it's below the plane x plus 2y plus 2z plotted here, I can get its intercepts, right? Plug in x and y equals 0, I get z equals 1. X and z equals 0, and I get y equals 1. Put y and z equals 0, I get x equals 2. So those are the intercepts. And that tells me here's the tetrahedron. It's underneath this plane, and in the first octant, it therefore has this region of projection in the xy plane that goes from 0, 0 to 2, 0 to 0, 1 and back to the origin. That's the triangle in the plane region. That's the projection of this solid. The theorem we just had says that we can evaluate this triple integral to find the mass of this object. And by the way, if we put 1 in here and integrate 1, we get the volume. So if you just ask to find the volume, just write the triple integral of 1 and the problem's set. We'll apply theorem 1 to say the triple integral can be evaluated as the iterated integral. 3 integrals. Integral of an integral of an integral. And on the inside integral, we have to go from the bottom surface. Z equals 0 is the bottom plane, the xy plane, so we integrate from 0 up to the top plane. It has equation, well, x plus 2y plus z equals 2. Translates to z equals 1 minus y minus 1 half x, right? We just solve this for z, and the top surface is z equals this. So z equals this to z equals this are the integration endpoints on the inside integral. And we just have to do a double integral between these two endpoints. Well, the inside integral of x with respect to z is xz, right? And then z has to plug in the bottom the top endpoints and take the difference, and so you get this. We've shown that the triple integral is equal to this double integral of x times the value of the inside integral, x and y treated as constants. So now, to evaluate this, we already have this method. We did this for double integrals. To evaluate this, we hope it's a vertically simple or horizontally simple region. If it is, and it is, actually either one, we can say x goes from 0 to 2, and y goes from a bottom curve, y equals 0 to a top curve, y equals 1 minus 1 half x. That says it's a little bit off, cut off this time by the copying machine, unfortunately. That means to evaluate the double integral over this vertically simple region from x equals 0 to x equals 2, we put min x to max x. Then we put the bottom curve to the top curve, 0 to 1 minus a half x. The integrand dy dx. This is a double integral with the inside integral x treated as a constant. So we integrate this with x as a constant, we get x times y. With x as a constant, we get x times y squared over 2. With x as a constant, we get 1 half x squared y here. So those are the three terms. We evaluate them at the top and bottom endpoints by plugging in this for y, right? Everywhere you see y, you put in 1 minus a half x squared. 1 minus a half x. And now if you evaluate this integral, I've left out the details. You come out with 3/5, it turns out. There is the value of this triple integral, 3/5. This is a good example. You'll see some similar ones in the text. They're all like that. You find the top surface, the bottom surface. You rewrite your triple integral as a double integral of the integral from the bottom surface, c equals this, to the top surface, c equals this. That allows you to rewrite your problem as a double integral that you use evaluate by your old methods. Unfortunately, you can see these things can get very complicated very quickly. It behooves you to write this in a nice coordinate system. If this solid has some sort of radial symmetry or other symmetry, you may want to choose a convenient coordinate system. So let's say you have some sort of radial symmetry. Maybe we want to use polar coordinates for the double integral when we're done. How can we do the double integral in a triple integral, or just in a double integral, using polar coordinates to make our integrals simpler? Well, we'll say a simple polar region R is a region R where theta is bounded between two constants, alpha and beta, and you don't go more than one rotation around unless you overlap the solid. So beta can't be more than alpha plus 2 pi. And then R goes between two surfaces, R1 of theta, two curves, R1 of theta and R2 of theta. So here's the picture. This black region here, R, is a simple polar region. It goes between a ray, theta equals alpha, a ray, theta equals beta, and two curves, R equals R1 of theta, R equals R2 of theta, given in polar coordinates. This shaded region here. How can we evaluate that? Well, we bound that between a curve, the ray, theta equals alpha, theta equals beta, and let R go between two fixed values. And so we have this red region that's partitioned up into little pieces of sector. A sector is like a slice of pizza. It goes between two rays and R between two constant values. And so we break up each one of these little subregions is inside a bigger sector and then outside a littler sector. It looks like this. And we can evaluate the integral over these little plane regions where each one of them is a sector minus a sector, a little piece of a sector. We'll say that has area delta AJK. And what is going to be the value of a double integral, meaning integrating over all these little small plane regions that are this shape? Well, we'll say delta AJK is big sector minus little sector. Maybe you remember the area of a sector is 1/2 r squared theta, where r is the radius. Well, the inside radius here and the outside radius here are, if we put rj star as the point halfway between the two fixed radii, rj star is 1/2 rj plus rj minus 1. And then we have to add 1/2 of delta rj, the width of the change in r. And here is the area of the big sector, 1/2 its radius squared times the angle it subtends, delta theta k, minus minus the area of the inside sector, 1/2 its radius, which is the radius here minus half delta Rj squared delta theta k. You don't have to be familiar with all the details. This is just to show you why it works. I'm deriving the formula. Well, if you multiply this out by squaring, and you multiply this out by squaring, 4 of the terms cancel, leaving only these two terms that add up to Rj star delta Rj delta theta k. So that's the area of delta Aj. To evaluate the double integral over this simple polar region, the black one here, then, we can take the double integral of whatever function is there, replacing x and y in the original integrand with r cosine theta and r sine theta dA. And then the double integral dA means limit of the sum, delta Ajk times f, right? Where delta Ajk is what? It's not delta Rj delta theta k. It's, according to this prescription, the area of the region is Rj star delta Rj delta theta k, because it's not a rectangle. So now we need to integrate this, but this part now becomes the integrand, and so we're integrating, if we rewrite this in definite integral notation, f times r, and the delta Rj delta theta k becomes a dr d theta, and the limit of the sum becomes the two double integral signs, and this is the double integral that adds up this limit of this sum, f times r delta r d theta, limit is delta r and delta theta go to 0. This is the double integral that evaluates what we want here in polar coordinates. Oops. Okay, sorry. Set the wrong end here. Now the theorem is that we've just shown the outline of, that for a simple polar region with continuous f, the double integral over that simple polar region of f can be evaluated as an iterated integral, f, x replaced by r cosine theta, y replaced by r sine theta, r dr d theta instead of dr d theta. And go between the outside curve and the inside curve, and between two rays, theta equals alpha and theta equals beta. Here's an example. Suppose I want to integrate over a very nice region that's a quarter annulus here, right? It's a quarter of a ring, that is. It's got an outside radius of 4 circle, x squared plus y squared equals 16, and an inside radius circle of 2, x squared plus y squared equals 4, and then these bounding lines along the x and y axes. Suppose I want to do a double integral of x plus y over this quarter annulus. Well, the shape immediately suggests I use polar coordinates, because look what happens when I plot polar coordinates. R goes between a fixed number 2 and a fixed number 4, theta goes between 0 and pi over 2, and both variables go between constants. So if I write this as a double integral in polar coordinates, it will have very easy integration limits. Here's what we get. We get integral theta going from its min to its max, 0 to pi over 2, r going from the inside curve, which is r equals 2, to the outside curve, which is r equals 4. X plus y gets replaced with r cosine theta plus r sine theta, and the dA gets replaced not by dr d theta, but by r dr d theta, the little area element for polar coordinates. Well, let's see, this times this is r squared times cosine theta plus sine theta, that's the integrand, dr d theta. And now I recognize that since cosine theta plus sine theta is treated as a constant of the inside integral and multiplies everything, I can pull it outside the integral because it's a constant, right? So I'm going to pull it outside here and integrate d theta over here. And then I recognize, furthermore, the remaining integral, r squared dr on the inside, goes between the two constant endpoints, no theta in there. So this integral in the middle, r squared dr from 2 to 4, is a constant. I can slide it out the other end and rewrite this as a product of two integrals, cosine theta plus sine theta d theta, integral r squared dr. each of them between the constant endpoints, and these are easy calculus one problems, right? R squared integrates as r cubed over 3. Need to plug in 2 and 4 and take the difference. Cosine theta plus sine theta integrates as sine minus cosine. Have to input 0 and pi over 2 and take the difference. This one comes out to be 2. This one comes out to be 4 cubed over 3 minus 2 cubed over 3. The whole thing is 112 over 3. This particular one's in your textbook. You might take a look at it. There's enough problems, I think, to get you through the triple integral section. If I have a triple integral now, and if I have the inside integral, there's some nice plane region R that has polar coordinate symmetry, then I can do the double integral that remains in polar coordinates. This is section 15.3. You shouldn't need this for the homework yet, but we'll do some more of these next time.